It's not the biggest object in the solar system, but it's by far the closest. So the moon, which is 385,000 kilometers from Earth, radius centroid to centroid. What's the next thing? What's the next body in the solar system that's going to influence Mars? Not quite, no. The sun. The sun. The sun is 150,000 kilometers, 150 million kilometers, much farther than the moon, but of course much more massive. And so that's why it comes in as a close number 2. It's a close second to the moon. When it lacks in distance, it overcomes its sheer mass. What's the third thing in the universe, or in the solar system? In the universe. That influences and tugs and tugs. Beautiful, perfect circular and elliptical orbits out of whack. The third thing. Not Mars. Mars is chasing. It's tiny. What's the next biggest thing in the solar system? Jupiter. And then everything else is kind of in the noise. Usually inconsequential enough where you can ignore it. These are the 3 big ones in this order for Earth-based satellites. If you start doing deep space missions, it's usually these 2 things. And depending on where you are in the solar system, it'll swap order of importance. Jupiter is almost, it's not as massive as the sun, it's farther away, but it's almost like its own star. People who study planetary solar system formation suggest that Jupiter is a would-be star. You know, a lot of stars are binary in nature. In other words, the solar systems of other places are 2 or 3 stars. And we have a single star system, which is not unheard of, but quite often there's another object that turns into a star. Jupiter just didn't quite make it in our solar system. Didn't quite make it. Okay. Now, this is a source of perturbation for Earth-based satellites, other bodies. There's another source of perturbation, and that is actually the Earth itself. Earth irregularities. There are 2 types of irregularities about the Earth itself that influence this satellite. Alignment with the latitude of the Earth that it started on. And over time, even slight changes, remember these things are moving at thousands of kilometers per second, right? And so if you impart even a slight error, like half a meter per second, builds into your velocity. Over time, that satellite will drift out of its design longitude and place in the sky. And you'll lose the whole reason why you launched a geostationary Earth orbit satellite to begin with. And so there are, because your phase launch in the Earth, you know, if you were in a lower Earth orbit satellite, this wouldn't be a big deal for a lot of reasons. First of all, you're always moving, so you're going to have to deal with some tracking anyway, right? Secondly, you're moving around and around the Earth, and whatever irregularities are on the Earth will kind of cancel each other out over time. Not true for the geostationary Earth orbit satellite because you see the same part of the Earth all the time. So there's an irregularity, a higher density region on one part of the surface of the Earth than the other. Over time, that irregularity will build error up into your orbit. And so it turns out that there are actually two stable points, regions of high-density mascons that attract a geostationary Earth orbit satellite, and then two unstable points. Let me just write where they are. The unstable points are at 162 degrees longitude and 348 degrees. These are unstable points. And then 75 degrees and 252 degrees, these are stable points. Okay, we're drawing this in terms of longitudes, so 360 degrees or 0 degrees, this would be Greenwich, England, roughly. So over here you have North America. Here's North America. Here's like Central Asia, India, Pacific Ocean, and Europe over here. Europe and the Pacific Ocean, very repulsive. North America, Central Asia, attractive, right? I'm just kidding. But that's where the stable and the unstable points are. If you have a geostationary Earth orbit satellite here, over time it will slowly, without any correction, start to drift over to this stable point. You find the satellite. If it's over here, it moves this way. If it's over here, it moves this way. It'll probably oscillate a few times before it gets there. Likewise, if it's over here, everything will start to approach that stable point over there. And if left to their own devices, over the course of many centuries, you would develop these two giant trash stars over the Earth, where all the dead satellites would accumulate. But obviously we don't see that. So as part of an international agreement, if you launch a geostationary Earth orbit satellite, before the satellite dies, you need to make sure there's enough station-keeping fuel to launch it into something called a graveyard orbit. And so that you only need to go about, 200 kilometers beyond geostationary Earth orbit. There's no frag up there, so you're going to stay in that orbit in perpetuity. And that piece of space junk will have just enough motion, slower than the surface of the Earth, so that all the mascots will integrate out and it won't fall into those stable points. So if you launch a geostationary Earth orbit, you must make sure there's enough station-keeping fuel to put it in that graveyard orbit. Any questions about that so far? Okay. Now, a couple other things to keep in mind when we talk about these extra bodies that influence the tug and pull of satellites in orbit. I said earlier, we had a really good question earlier, well, are all the things in the solar system lined up on a plane? The planets all operate on the same plane? There's nothing to, kind of. But there are some disturbances. So let me sketch out two systems to show you kind of what the angular disturbances are. They're not going to be to scale, but they're just for reference. So let's say this is the Earth, and this is the rotational axis. Not to be confused with the magnetic axis, which is slightly off. But this is the geographic North Pole, and this is the geographic South Pole. And so 90 degrees to that would be the equatorial plane. I've drawn it as a line. It's a plane that comes out of the board and is perpendicular to that rotational axis. Now, a geostationary Earth orbit satellite, we said, had to be on that plane to be geostationary. You can launch satellites at different angles in different planes, and that plane is called the plane of inclination. So when we talk about inclination, we're measuring the angle of an orbital plane from the equatorial plane. 0 degrees would be equatorial. You can go all the way up to 90. That puts you on the poles. You can even go past 90. If you've gone past 90, we call that orbit retrograde. Because effectively what you're doing is now rotating against the rotation of the Earth. Those are actually the more expensive orbits to launch into, because not only, usually you launch everything going with the rotation of the Earth, because you get a little bit of a boost of kinetic energy. Because you're starting out on the Earth, and you're rotating in that direction already, it makes sense to kind of launch it in that direction. Otherwise you have to overcome that kinetic energy and then add that kinetic energy back, and then launch it into enough, give it enough energy to launch it to an orbit. And so from when everything is, most things are in a inclination launch of less than 90 degrees. There are some applications, we'll learn about a couple of them, where you want to launch in a retrograde orbit, have things go against the surface of the Earth, or the rotation of the Earth. So anyway, this is inclination. The Moon, the natural satellite of the Earth, is at an inclination of 5 degrees. This is why we don't get those solar eclipses that often. Because usually this isn't even lined up with the solar orbital plane. And so then if you go down and look at the Earth-Sun system, actually has an axis of rotation. And it's roughly lined up with the plane of the solar system, but the Earth is actually 7.3 degrees inclined from the Sun in its orbit. And then the Earth itself, of course, has a tilt of 23 degrees. Its axis of rotation is actually 23 degrees off from its orbital plane with the Sun. And of course the Moon is going to be plus or minus 5 depending on where it is in the system from that. So it's going to kind of wobble around. But only when things kind of line up perfectly do you get things like lunar eclipses and solar eclipses. That's why they don't happen very often. Not every month, every period of the Moon. So these are the basic irregularities that affect our orbits or influence our orbital designs around the Earth. Now, I'd like to kind of conclude this section by talking about a concept called orbital forcing. It's kind of a nice way to tie everything together geometrically, all the things that are going on in a complicated three-dimensional orbit. And it also turns out this is a kind of an interesting topic because it influences long-term climate change, which is a big research topic nowadays. So, kind of shows you not just the man-made, but also some of the natural things that influence climate over time. And so these all fall under the topic of orbital forcing that I'm going to talk about. We use a lot of these concepts. These are actually irregularities in the orbit of the Earth about the Sun that causes some things that influence the climate of the planet. And I've highlighted 4 things just to show you. They're very similar to things that orbit around the Earth or satellite orbits around any irregular object. Now, orbital forcing, many of these perturbances are due to the presence of Jupiter. So if we're talking about an Earth-Sun system, the Sun is the biggest thing in the universe, and that's usually the culprit for disturbing other orbits. But if you're orbiting it around the Sun, Jupiter is the next biggest culprit, right? And so the presence of that heavy extra body introduces some irregularities into elliptical orbits that disturb the climates. And in fact, because these are quasi-periodic, there are certain climates in the long-term cycle of Earth. They're called Milankovitch cycles. This is